P-values are everywhere in scientific papers. But what does a p-value even mean? And why is it so special if it's less than 0.05? In this video, we'll explain how p-values help scientists make conclusions. For example, in this 2006 paper, scientists were studying weight maintenance in mice and the impact of the microbiome on weight gain. The microbiome is the collection of microbes that live in or on an organism's body. The scientists had shown that the gut microbiome of obese mice had a different composition of bacteria than the microbiome of lean mice. But they wanted to know if the bacteria in the microbiome was the result of the difference in weight, or if the microbiome caused the difference in weight. To test that, they took mice that had no microbiome of their own, and they did a fecal transplant. Yeah, you heard that right. They took feces from lean or obese mice, and they placed the fecal bacteria inside mice that had no bacteria of their own. 2 weeks later, both sets of mice had gained weight. The bacteria helped the mice get more energy from their food. So the question is, can we conclude that the microbiome from obese mice makes the mice gain more weight? Yes, we make that conclusion. The bar is higher, the gains more weight. What's the alternative explanation? That they're not actually different? What do you mean that they're not different? The bar is higher. Of course they're different. Let me give you another example. I had this idea once that people's height depended on their last name. What? So I thought maybe people whose last name starts in the second half of the alphabet, maybe those people are on average a little bit taller. I know, but it's a testable hypothesis. So I did an experiment. I asked people on Twitter to tell me their height and the first letter of their last name. And look, according to the data, people whose last name starts with a letter in the second half of the alphabet are on average taller. But that's ridiculous. You only had 2 people in each category. Like, you just happen to get 2 tall people in the N to Z category. Well, how do you know that though? How do you know it's chance? I mean, we know there's a difference in their last name. Well, what did the data look like when you had more people? Okay, so when I looked at more data, the difference between the groups got smaller, but it was still a difference. But I mean, still, like, maybe you just had some tall people in the N to Z category just by chance. Like, that's possible, right? Exactly. That's what p-values help us do. They help us tell the difference between random chance and a real difference between the groups. So, going back to the mice, how do we know whether this difference is due to random chance or due to the different fecal transplants? I mean, if you took 100 mice and weighed 10 of them, their average weight would be different than if you weighed another 10 mice. But that's just because of random chance. Now, if I told you that these 2 groups received different fecal transplants, then you might think that the difference in weights is due to the fecal transplants. But what if the fecal transplants have no effect? I mean, we know that if you take 2 different groups and weigh them, you'll get slightly different averages, right? So how do we decide whether this difference in weights is due to random chance or due to different fecal transplants? The p-value helps us decide between these 2. In statistics, these 2 possibilities have names. The null hypothesis is that the 2 groups are actually the same, but you see a difference in your measurement just because of random chance. The alternative hypothesis is that the difference in weight is not due to random chance, but rather due to some real difference in the characteristics of the 2 groups, like which fecal transplant the mice got. In statistics, we call these 2 possibilities the null hypothesis and the alternative hypothesis, but they are different than the scientific hypothesis. In this case, the scientific hypothesis is that the microbiome of obese mice contributes to mouse obesity. Just because they're both called a hypothesis doesn't mean they're the same, so don't mix them up. So to answer the scientific question, we need to know whether this difference is real or just due to random chance. To distinguish between these 2 possibilities, we use a p-value. A p-value is a number that is calculated using a statistical test. There are lots of different statistical tests that can be used on different types of data, but each statistical test has an output, which is the p-value. The p-value is a probability. That's what the p stands for. It's the probability that the observed difference could have happened if the null hypothesis were true. For example, imagine that we have a lot of mice and we weigh 2 groups of them. Let's assume the 2 groups are not actually different. Remember, that's the null hypothesis. So when you measure their weights, the averages are not exactly the same just because of random chance in which mice got measured. But that's normal. In fact, the probability of getting a tiny difference is actually quite high, even if there is no real difference between the two groups. That probability is the p-value. It's usually expressed as a fraction instead of a percentage. Now, if you measured two new groups, the averages would be different, and you'd have a different p-value. Now, let's say you measure two groups and the p-value is small. That means getting that result is pretty unlikely, if the null hypothesis were true. So that's when you say, maybe in this case the null hypothesis is not true. So these data are better described by the alternative hypothesis, that the groups really are different. But the p-value can be anything, right? From low to high. So how do you know when it's low enough to reject the null hypothesis? That's a great question. Scientists tend to reject the null hypothesis when the p-value gets less than 0.05. To explain why p-values less than 0.05 are so special, let's play a card game. Have a seat. Okay, here's how it works. I'm going to flip over one card at a time. Every time I flip over a black card, you get a bar of chocolate. Every time I flip over a red card, you owe me $1. Okay, I mean, I like chocolate. All right, let's play. Okay, $1, huh? All right, here's $1. All right, another $1. Come on, come on, come on, come on. Oh, come on. Nope, There's something wrong with your deck. It's rigged. Your deck is rigged. You're right, it is. When you started the game, you assumed that the deck I was using was a normal deck. That was your null hypothesis. The first time you got a red card, that didn't tip you off because if the deck I'm using is the same as a normal deck, there's a 50% probability that you'll get a red card. That's a pretty high chance, so you weren't suspicious yet. The second time you got a red card, you still weren't suspicious because if the deck I'm using is the same as a normal deck, the probability of getting 2 red cards in a row is 25%. That's a 1 in 4 chance, which isn't that unusual. As I kept flipping over cards, the probability of getting that many red cards in a row, if the deck I'm using is the same as a normal deck, kept going down. You started getting suspicious, but you weren't sure yet that it was a rigged deck. Finally, when I flipped over the 5th red card, that's when you said, there's something wrong with your deck. Because if the deck I'm using is the same as a normal deck, the probability of getting 5 red cards in a row is 3%. And because that's so unlikely, I thought, I don't think the deck you're using is a normal deck. Yes, that's right. Because getting that result, if the null hypothesis is true, is so intuitively unlikely that that's when you rejected the null hypothesis. So if the p-value is the probability of getting a result if the null hypothesis is true, then if the p-value goes less than 5%, for p-values we use fractions, so 0.05. We reject the null hypothesis and conclude the alternative. Yes, that's right. And let's be really clear, it's not like there's something magical that happens when you pass the 0.05 threshold. 0.049 is really similar to 0.051. Because it's just a probability. Exactly. Remember the mice? The mice that received the obese fecal transplants gained more weight. But was the difference in weight just random because of slight differences in the mice they chose? Or was it the result of the fecal transplants? The scientists used a statistical test called a t-test to calculate the p-value. And in this case, the p-value was less than 0.05. So the scientists rejected the null hypothesis and concluded that the difference between the two groups of mice was real and likely due to the fecal transplants. I mean, isn't that cool? The bacteria inside a mouse can affect how much weight it gains, which might be true for humans too. But don't try a fecal transplant at home. Besides being able to transmit diseases, poo is a lot harder to work with than p values. No, no. Such a bad joke.